Hey there. What I was going to do in this video was to show you how to create a black hole so that you could make a wormhole and tunnel through space-time to other dimensions, other galaxies, across continents, under the ocean. Instead, I'm going to show you how to make these, which is the stanchions for the primary for the Tesla coil. Okay, so what we're going to do is we're going to take this refrigeration coil of refrigeration tubing and create the primary for the Tesla with it. Now what I'll do is let's take a look down here. Here's my old primary, the old coil. It's not exactly pretty, but the idea is that this refrigeration tubing is laying in these C-shaped grooves. It's not drilled in, it's not held in by anything but friction and these C-shaped grooves themselves. Now what we've done is created a hole that doesn't go all the way through. It just makes a C, but it is slightly more than halfway so that the tubing snaps in. Now the copper tubing is somewhat resilient, or let's say somewhat flexible. It's very flexible, but it's very, very slightly springy. If you press it and spring it too much, it'll deform. And so if these C-shapes are closed a little too much, like some of the test holes I have here, you know, for instance, if we were to take that one, that's closed a little too much. This one's closed a little too much. So is this one here. When you try to lay the tubing into it, the tubing will, you could force it in there, but the tubing will turn into, instead of being round, it'll be an oval shape once it gets in there, and it won't snap. It'll pop out again. So what you want is just enough of a little lip so you can get it to snap in and stay and not deform. Now, what I wound up doing was I created this little test jig here. Let me move you out here. I created this little test jig by taking my drill press, actually it's a mill, and using an end mill, 3/8 inch end mill. We're using 3/8 inch copper tubing and drilling various depths, and as you can see, you know, everything from almost completely closed to hardly there at all. And what I wanted to do was to take the tubing and then attempt to snap it in. And what I discovered was that with a lip about 50 thousandths of an inch past exactly center, so if I was to say I wanted to drill the hole and have the bit halfway so that only half the hole was drilled, I went 50 thousandths past that and I created a little tiny lip. It's almost imperceptible, but it is there. And the effect that you get is this. You can probably hear it if I hear that. The tubing snaps in place, and now it won't come out. Okay, so again, like the effect we want here is I'm going to take this and press it on there, and you hear how it snaps? So what's going on here is the copper is not deforming. If you make the hole too deep and the lip is too deep, like pick one of these over here, say, let's see if we can make sure we got it in focus. So what I'm saying is I'm going to drill in, and then I'm going to move downward 50 thousandths of an inch. That's 0.05 of an inch. By doing that, we get this effect. So the tubing is, you know, you can bend this tubing very easily and you can deform it. And so what you don't want to do is you don't want to create a situation where the hole is so narrow, the opening is so narrow that on the way in the tubing deforms. Then it's going to stay deformed and it'll pop right out again. But at 50 thousandths, you hear that? Let's see if we can do it over here. At 50 thousandths of an inch, there you go, it snaps right in and it comes out and it doesn't deform. Now the thing is, that'll hold it in there. That will hold the tubing to this stanchion when it's mounted. So what I want to show you here is a couple other ideas for creating the primary. This is the first one I ever made, and I would absolutely not recommend doing it. This is hanging up on my garage wall here, which is probably where it belongs rather than on a Tesla coil. As you can see, what I did was I had manufactured 6 of these L-shaped stanchions, and I drilled, I believe, 13 holes in each one, and the holes are complete circles. So if we zoom in here, we can see they're just completely closed holes. And that's 1/4 inch refrigeration tubing that's run through there. And the question that you may have in your mind is, how the heck did you get the refrigeration tubing through there? Well, I wound it through like lacing a shoe. That took me, getting that tubing through 13 turns took the better part of a day. It was physically taxing. I wound up with blisters all over my hands because, as it turns out, the tubing slides through 1 or 2 holes no problem. But as you go through hole after hole trying to create a spiral, the friction that each hole presents multiplies. So by the time you try to get this thing through 13 holes times, 13 holes times 6, you wind up with so much friction that the tubing hardly moves at all. You wind up scooching it, as you will, if you will, a couple millimeters at a time, and it is extraordinarily difficult to do. Now, the first Tesla coils I built had very loosely wound secondaries. The frequency was very, very high. I needed, 10 turns on my primary, and I didn't know what I was doing. So I created it this way. And those plastic, it's not lucite, it's polycarbonate L's, are glued to a polycarbonate circle, much like the one I have on my first Tesla coil that you've seen pictures of. And they're glued with acrylic cement. All the stuff's available at Tap Plastics. Again, I would never recommend doing anything this way. Having the tubing resting in a C-shaped groove is a much better way to do it. Now, there's another type of primary that I haven't quite figured out what to do with these yet, but there's an example of a ribbon primary. Now, that's not, that metal is not made to be the primary of a Tesla coil, of course. That metal is for copper roofing, and you can buy this online. And what we did was I took the copper roofing material and I interspersed it with some weather stripping. I believe there's an individual online, one of the guys from the Tesla coil mailing list has a video to show you how to do this. That worked quite nicely. The turns tend to be very tightly wound together. You can use Java TC to figure out the correct length and the number of turns you need for that. The reason I abandoned it, I wasn't having any particular problems, but some of the guys on the coil mailing list, having used this type of primary before, had all sorts of difficulty with racing sparks and whatnot. So I went back to the round refrigeration coil primary. So I've managed to manufacture 4 of these stanchions already. I need 6, and I'll drill the last 2, showing you how to do it. I wanted to make sure I had the process down before I videoed it. So what you see is I've got enough space for 1, 2, 3, 4, 5, 6, 7 turns of the coil. Java TC says we only need 4, but I'm pessimistic, and if we need more, I've got it. I don't know how the resonance is going to be, how the frequency is going to be affected by the fact that the new platform we're putting it on is made of aluminum. If it affects it that much, it's probably not going to work at all, because those transistors won't work above 70 kilohertz or so. They're only spec'd to work at around 30. The fact that we can get them to work at all at 70 is amazing. So if we start putting in 7 loops of primary, that means we'll be raising the F0, the resonant frequency, quite a bit, and it won't work at all. But at any rate, it was easy to drill 7, so I drilled 7. Let's see. Okay, so what we're using is, let's get out to here. Let's take this bit out. So what I'm using is an end mill. Now, this is a 3/8 inch end mill. If you try to use a 3/8 inch drill bit, you may have a problem. Now, again, I'm using a mill. I've got this whole thing set up. Before I had a mill, I used a drill press. Before I had a drill press, I just built a jig on the ground with wood and used a hand drill. The problem you're going to have trying to make C-shaped holes like this with a regular drill is measuring. It's going to be difficult. And the second thing is, as the drill bit goes through, what you're going to find is a regular drill bit will tend to flex. and so it's difficult to get the holes exactly parallel. The coil of wire is going through there, not wire, but tubing is going through there in a curved way anyway. So in some sense, flaring the ends of these out is not such a bad idea, although you don't have to. But if you're going to use a regular drill bit, my suggestion is don't. You can buy these things online on eBay. This is called a 3/8 inch end mill, and you could just chuck that up into your regular drill, into a hand drill, and at least it would be stiff. It won't flex on you, and you could probably put it in a drill press as well. The problem with the drill press with a Morse taper is that when you start cutting through and one side's open, there's going to be a tendency for the bit to want to flex outward, and when that happens, you get an asymmetric force on the Morse taper, and the whole chuck may fall out, which has happened to me many times. So you got to watch out for that. In any case, now I've got a mill. I'm doing it this way. I'll show you how I did it. Okay, from the prior video I showed you I made these, cut them on a tile saw. They are square, and they're of equal width to the best of my ability, and they're equal length to the best of my ability. Which means when I chuck them up on or rather mount them in this vise, the fact they're square and the fact they're the same size should really allow me to tighten this thing and not have to worry about any unevenness. So what I'm going to do is put in an edge finder. Well, first let's do the following. First let's get these guys in there. And does more light help? Nah, more light seems to be worse. Now, also what I've got, you can see on here, I've got one in there already. This is just a sacrificial piece that happens to be exactly the same size. It's just a spare one. I've got these on 2 parallels, and the problem is when the drill pops through, it tends to splinter. So if you've got this piece down there, it'll make a nice smooth hole. I've also got my little end stop there that I made. And what I'm feeling for now is just to see if I can keep them parallel and get them wedged in there nice, so that we can repeat the holes we did before. Alright, they're not even on this side, but they are on this side. And this bottom one doesn't count. Alright. So I'm going to take this edge finder and I'm going to turn on my DRO. Actually, it's in a pretty good place compared to where it was last time. It hasn't moved at all, but I'm going to be pessimistic about this, and I'm going to realign it. Got to loosen up the X table. There we go. And let's see if I can get you in there. Now, were it not for the kindness of the machinists online, Keith Fenner and Adam Booth and Tom Lipton, I would never know how to do this. But what I'm going to do is I'm going to find the edge here with this edge finder. And we do it the way they prescribed. Maybe going a little too fast. and we go till it lines up and just pops out. Okay, that should be the edge. And if I zero my X, and I shouldn't zero the X, actually I got to go 1/10 to really center it. So we go 1/10 of an inch, and now I zero my X. That should be right on center. So let's take this guy out, put the bit back in, put the end mill back in rather. That's not too bad. You're at an angle, but I'm not. And that looks like it's right on center. So what I'm going to do now is I'm going to move this 50 thousandths. 50 thousandths with this, which is 5/100ths of an inch outward. And I'm going to lock the table. Lock it down that way, and then I'm gonna wind this, make sure that's tight, wind this back to this close to the start. Let me get a better angle on it for you. Alright, let's make sure that's using one of these as a template. I'm going to try to drop, whether or not we are, a couple of hundredths in or out on this measurement, front and back is not so critical, but because we'll be able to adjust it once it gets on the table itself. All right, so if I put that there, is that lined up? There we go. Oh, in fact, not bad. We're within 7 thousandths. This wouldn't be good for metal machine work, but for this, it's going to be good enough. All right, let's see how where we are. All right, let's get the glasses and the mask on and do some cutting. Now the holes are 3/4 of an inch apart. I got a 0.75 on the DRO. Away we go with hole number 2. Just for grins, let's make sure that lines up with the next hole. And it does, and we're happy. And there we go, all 6 of them. Holes lined up. And we'll be able to snap the tubing into there. Now the next step is going to be to drill and tap on the back side for some 1032 screws. So I drilled each of these stanchions with a number 21 drill bit. I'm going to tap them for 1032 screw for no particular reason other than it fits, and I have a lot of those screws laying around. I didn't video drilling all these holes. That would be pretty boring. Bah! Little that's probably a machinery joke as old as the ancient Greeks themselves. But what I'm going to just do is I'm just going to try tapping this. I'm going to use the mill as a guide. I won't go through tapping all of these things because the truth of the matter is that would be about as boring as watching paint dry. But just to show you, this stuff taps pretty easily. I should not have any problem at all. I'm using a bottoming tap. I've drilled each of these holes about an inch deep. I won't go in that far. I'll only go into the extent of the threads on this. I don't really need very much. There's not ever going to be very much pressure on this. It just needs to be able to hold those the coil steady, the coil of primary tubing steady, and that's not going to move around very much at all. In fact, the most that's going to happen to it is it's going to get hot. So that's the most of my worries. Anyway, as you can see, it goes in pretty easily, and as long as I keep pressure on this, it should not strip. And so as an old manager of mine once said, "What have we learned here, Grasshopper?" Well, what I've learned is a potentially useful lesson. So this material is very brittle. What I tried to do is to use a tap like this, which I guess you would use for plastics or some springy material that you could cut into. It's a bottoming, and what happened was it just stripped. So I was using a 10 by 32, and it just stripped straight out. So this is bad for this stuff. I switched to one of these. This is a spiral flute tap, and I actually upped the thread size to 1/4 by 20. I wanted to get deeper threads because, again, this stuff is so brittle it'll crack. So I think the thin threads on the 10 by 32 are a bad idea. So what I've done is I'm using a 1/4 by 20 spiral flute tap, and I'm actually just able to twist it into the same holes, to the 21 size, number 21 size holes that I drilled for the 10 by 32. That's how brittle this stuff is. You can just, those pilot holes will work even with a 1/4 by 20, which requires a number 7. So that's what I'm going to do from here on out. I'm going to put 1/4 by 20s in here. I have some plastic 1/4 by 20s. I don't know if the metal ones are going to make any difference in the construction of the coil. I've used metal before to hold these things in. It doesn't really matter, but that's pretty darn secure. So I think I'm going to switch to plastic. So I'm just using the dead center to give me a start on this thing so I don't accidentally start it in crooked. But once it's started, it goes just fine by itself. I'm just applying some pressure with one hand and turning with the other. I could have, I might have tried drilling it with a power drill, but my fear there is that this stuff is so brittle, if you don't use hand pressure and feel it, you'll probably strip it. I think the danger of breaking the tap is very low. It's very soft stuff, but I think the possibility of stripping the hole is quite high. So that's why I'm using the mill head. And as you can see, it makes a lot of dust. So I've got to clear the hole. But once it's started, it goes pretty smoothly. But again, I got to do this. Oh, let's see. Got to do this 14 more times after this one. I won't bore you with that. Alright, so drilled and tapped all of these for 1/4x20s. Now I've got plenty of these, you know, regular old stainless steel 1/4x20 bolts, many sizes. But I also have these nylon ones. And I don't know, I may use the nylon ones just because they're non-conductive, and there's probably no particular danger in having them be conducted because they won't be connected to anything. On the other hand, you know, want to make as much non-conductive as possible. So the idea is that these guys will be spaced at 60-degree intervals. You know, roughly so. And the coil will we'll mount the coil, and then we'll snap in the tubing into that. So the next step after this will be I've got to cut holes in the in this plate somehow at 60-degree intervals to allow for these guys. And I've also got to cut some holes to allow for the tubing connections, the electrical connections to the tubing themselves. If you look at this one back here, you'll see that you know, you've inevitably got to connect it up to the high voltage source. This one is connected here and here. If you can see that, it really doesn't matter. So I'm going to have to cut holes in there for the high voltage source, and I may have to cut the holes in a way that allow me to tune, because the chances of my Java TC calculation being dead nuts on, the chances of that being dead on are pretty small. It won't be too far off. It's saying I'm roughly 3.8 turns, but I may wind up going up to 4.5, you know, depending on how much interference or effect I get from, you know, the fact that this base is metal. I may wind up having to do some different tuning. So I need to allow for the fact that I may need to adjust the tuning point around the periphery here. So I'm going to have to cut some slots that allow me to bring the high voltage up. So there's one primary slot for the high voltage on the inside, and then I need another traveler to come out. So I've got to dismount that and router out some grooves. So that'll be the next thing. And maybe in between doing that and getting the coil set up, we'll build some black holes and we'll teleport to other dimensions, or perhaps we'll get into quantum field theory or something like that. Anyway, see you next time.